We now build a better model for hard disks, and here in this model we have essentially only two parameters. So we have a memory size M, so that's the internal memory size, and we have block size B. So here we're assuming that the disk has been divided into blocks. So you have huge disk over here, has stores, let's say, n numbers, and you have put these n numbers into blocks that have b integers. So you have this block that has b on numbers, this other block has b numbers, etc. And this division is fixed. And what you care about in this model is how much you spend in your internal memory, and also how many IOs you read and write, how many blocks you need to read to the memory and write to the memory. And the only thing that basically we restrict here is that every time you want to read an element, let's say if you want to read this element in this block, you have to read the whole block to get that element. Okay, that's essentially the only difference compared to a RAM model. In other words, this model is very simple, but now the question is it realistic? Are we actually bridging the gap between theory and practice? There's actually a lot that goes into this model, and this idea of instead of reading one element, reading a whole bunch of elements, this is a very common idea used in many different places. And essentially it's a way to hide latency and to get to the optimal behavior of whatever we're doing. And I'm going to explain this here in this slide. First of all, there is this nice observation that if you have your block size to be relatively big compared to the track size, then you can ignore rotational latency. A track is essentially one data that can be stored in the one rotation of the disk. Okay, so let's say that's a track. It's a very imperfect drawing of a circle, but assuming there's a circle, that's one track. If the block size is larger than this one track, what it means here is that every time I want to read one block of data, I will need to read 5 consecutive tracks, right? So you will need this track, then the arm slightly moves this way, for example, then I read the next track, and etc. What happens here is that it doesn't really matter where the arm was, because if you're just going to read the entire track, you can just start from anywhere, right? So in other words, if this is my track, let me draw a circle. It doesn't matter whether I start to read the circle from here or from here. I just need to wait for one rotation until I'm done. Okay, so by this idea, we could ignore rotational latency. So the only thing that matters is the seek time. And if we set B to be 5 times the track type, and this number 5 can be verified or derived experimentally, then the seek time is marginalized. What this means is that the time it takes to read 5 tracks of data is larger than the time it takes for the arm to move to the correct location. Okay? Another way to look at this is that if I make a chart like this, where over here I have block size on this x-axis, and I have efficiency. What is the rate that I'm reading per second, right? So data transfer rate per second, right? So data rate on this x-axis. If you're just reading one integer here, then your rate is going to be abysmal, right? Because if you want to read some random integer over here, then you have to wait for the rotation and for the seek time to read it. So, you know, your rate, data transfer rate will be over here if you're just constantly reading random integers on the disk. But as you read more and more data, let's say if you read larger consecutive elements on the disk, or maybe this much data, your rate slowly goes up. It depends on how it goes up, depends on the exact architecture, but there will be at some point where this will plateau, which means that your hardware cannot transfer more data than this. And then you could cut off here and you could say that this is my optimal block size. Okay, if my block size is this much, then I'm transferring, my transfer rate is, let's say, 95% of the optimal transfer rate. Compared, so this 95% of whatever the maximum speed of data transfer rate that this hardware has. And in that case, we're actually not losing any efficiency in terms of transferring volumes of data. Okay. And there are a few more things that goes into modeling, and I'm not going to go into this, but basically this is the main part of the story. With this simple model, we can reasonably model the behavior of a hard disk. The only major thing that we have ignored here is this variable rotational latency. This thing I have completely ignored. Because technically speaking, still the case that the data that is stored here can be read much faster than the data can be stored here. But we're ignoring that, and you can kind of minimize this impact of this phenomena by storing the data only at the edges of the disk. And if you do that, then you could kind of ignore this behavior as well. Okay. And in the next video, I'm going to show you how we can use this simple model to analyze